hello everybody and welcome to another open class. We are today in open class number 190, getting close to that 200 barrier. Pretty soon, it will be pretty soon. But yeah, so today we are here in for checking a bit on perception for ROS2. So we are going to be doing line following using OpenCV for ROS2, so we are going to get to practice a little bit with the OpenCV library and understand some key concepts that are used in perception. So yeah, let's get started. Before everything, as always, let me know please if audio is fine, also the video is fine, so that we can keep moving forward without any issue. And meanwhile, let me just switch here to my computer screen very quickly. There we go. Let me get into my account to get started and open also here the open class. No, not this, sorry. I should get here the button. There we go. Okay. So hello, many people here. John, Eliesa, Christian, Stefan, Gilbert, also Tisas around here to help us with the class that he has helped creating. Gilbert says, audio could be a bit louder. Video is fine. Okay. Audio could be a bit louder. I can increase it a little bit there. But also from your side, I guess that you can also probably tune up the volume a little bit. All right, so yeah, if everything is fine, then let's get started with the class. Welcome, everybody. As always, I saw a comment there that Gilbert said that the project was not available. It should be available now. All right. So yeah, the very first thing that we have to do is to get today's class project. And as always, this is very easy. All you have to do is to click here in the button right above the chat, which says fork and open the class project. Okay. I'm going to click here myself to get my own copy of today's project. And then this is going to bring you to the main project page, as you probably already know. And here in the right side, you are going to have the streaming panel with the live stream, the chat, in case that you want to send any comment, questions, feedback, whatever you want. Write it down here in the chat, so I will be reading it. Then I'm going to move this out just to get some more space here for the project when it loads. Mine is finished loading right now. Here, in my case, it's open many things. It depends on your previous setups. But yeah, basically what you should be seeing is this, let me close everything, is this notebook here. Yeah, the notebook for today's class, Jupyter Notebook, which is automatically opened. And it's basically the guide that we are going to be using for today's class. Okay? So make sure that all of you are able to properly get this project and that you are able to also open it, of course, so that you can you can have access to the notes, to the notebook, to all the codes, etc. All right. And as always, also let me very quickly remind you that you are going to have a copy of this project in your account. Yeah, you can access it whenever you want. Here in the left menu in the My Project section. If you come here, you are going to see that you have a copy of the project, and this copy is in your account. Yeah, so you are going to be able to open it next week, next month, whenever you want, in order to revisit this specific ROS2 project. All right. Okay, then, yeah, before actually getting started, let me know, please, if everybody has been able to get the project, to open it properly, and so on. Here, in my case, I'm going to open the chat so that I can read you. So, any issues so far, any questions so far? Has everybody been able to get and open the project properly? Yep, no. All good. Says Gilbert. Also, Ivan opened. Okay, amazing. Then I guess that we are ready to get started. So as I was already introducing at the beginning of the class, today we are going to be checking line following with OpenCV for ROS 2. Okay, it's a pretty common concept in robotics, this line following. And yeah, we are going to see here how to create a basic line following algorithm for ROS 2 using OpenCV, which is going to allow us to review some interesting concepts related to perception. All right. Then, as in the last classes, we are going to continue using our BotBox robot. Yeah. So I have already talked about this BotBox in previous classes, but basically this BotBox is a lab in a box to teach robotics. It includes off-the-shelf robots, environment, the one that you are seeing here, which, by the way, as you can see, it includes some lines in order to be able to practice the line following algorithms and concepts and so on. It includes already built-in projects. So it's basically an educational platform that where you can use it in order to teach, and not only teach, but make the students practice with real robots, all the concepts that they are learning, yeah? And before getting started, I want to share a video with all of you about this BotBox. So let me click on the play button very quickly here. There we go.
How awesome would it be to provide your students with the experience of programming a robotic warehouse? Now you can with BotBox.
Robotics lab that we have designed it in order to help you and robotics teachers or robotics lovers all around the world.
BotBox is a robotics warehouse lab in a box that you can use to teach and practice robotics. With BotBox, you can provide your students with practical experience in programming robots for a warehouse.
But experience-based classes with minimal preparation, because basically everything
BotBox provides the robots, the environment, the simulations, and the projects for your students. With no installation required on your students' computers, you can have them practice ROS programming, robot navigation,
and even a gripper, so that you can also
robot perception with OpenCV,
etc. It also includes a small warehouse environment, which is already designed in order
behavior
to
trees,
practice several robotics concepts, such as
fleet management, mobile robot kinematics, and sensor fusion. Simple management of projects and connection to the robots. Everything powered by robotics cloud computing.
Practice all these ROS 2 concepts, all right? Then basically this BotBox package, okay. All right, yeah, so basically this BotBox package makes robotics education more accessible, allowing teachers to deliver practical robotics classes without unnecessary complexity. Okay, so I think Thesis is telling me that probably the video has taken, it had some audio, which I was not listening. Let me play it again. And
how awesome would it be to provide your students?
Close it here. So yeah, here in the notebook you are also going to find information, and we have added a link here that you can click in order to go to the BotBox page and get information. And if you are interested in it, you can order it also, of course. Right? So, yeah, having improperly introduced the BotBox, let's now go to the topic of today's class. So, what are line following robots? Then line following is a fundamental concept in mobile robotics where a robot is designed to follow a predefined line or path on the ground or surface. Yeah? And how it does that? Well, very easy. It does that by using sensors, typically a camera. Yeah? Then with the camera, we are going to be able to detect this line or path. There are different methods. We are going to be reviewing one of them today in which we can do this. But this is a very common concept in robotics, and it can be used for several more complex tasks, such as navigation, automation, or even education and research, because it allows to put into practice interesting concepts related to robotics, perception, computer vision, etc., etc. Yeah? Then, in our case, we are going to be using OpenCV, which basically it's a open source computer vision set of tools that are very convenient for analyzing, processing, extracting information basically from images. Yeah? And this OpenCV provides what is known as the CV Bridge package, which allows for a very easy and seamless integration with ROS. Yeah? We are going to be seeing all these concepts into code in a moment. Yeah? Then there are many ways in which we can use OpenCV in the context of robotics, and more specifically in the context of ROS, like image acquisition, image processing, line extraction, which is what we are going to be reviewing today. It can be used and applied to path planning and control systems, visualization and debugging, and many more. Okay? Then for today's open class, we are going to focus, the goal for this class is going to be able to create a program combining ROS and OpenCV that is able to detect a line in the floor. Yeah, here we have the simulated version. This is the real BotBox, okay? But in our simulated version, you can see that in the ground we have some blue lines painted here, okay? Then our goal is going to be able to create a program, a ROS2 node, that is able to detect these lines using the camera, which is available in the BotBox robot, and use this information, process it in order to generate some velocity commands so that our robot is able to follow these lines in the floor, in the ground, okay? So this is the goal, the mission for today's class. Then we are going to be creating this program all together, step by step, and reviewing all the different parts that we are going to be adding and integrating into the program so that we can successfully reach our final goal. All right? Then for this, the very first thing that we are going to do is to launch this simulation. This is a simulated representation of the BotBox environment, the real one, which you can see here. Actually, this is a simplistic simulation. Okay, so the one that we provide with BotBox, it's much more complex, okay, and it's much more similar to a real environment, but this is just a basic representation so that we can do some quick tests, for instance, for line following, all right? Then, in order to launch the simulation, we have to execute this command that you have available here in the notebook in the launch the simulation section, okay? Yeah? And then the very first thing that we need to do for this is to open a new terminal. So I am going to do this right now here. So let me open a new terminal. There we go. And then you can directly copy and paste the command here from the notebook. Actually, that's what I'm going to be doing. So let me copy it directly from here with Control-C and paste it here into the terminal with Control-V. There we go. Then this is going to start executing and running some processes. And eventually we should see the simulation popping up. And there we go. Here we have our simulation. All right. So this is the very first step. We have introduced our mission, our goal for today's class, and we have started the BotBox simulation. Okay? Yeah? So far, so good. Let me have a quick look here at the chat to see how you guys are doing. Oh, it seems that the video... it seems that the video was getting on top of my voice. Okay, my bad. My bad, sorry. I was configuring all this before the class, but probably I made some mistake. So apologies for that. Now you can hear me properly? Yes? I assume so. And please let me know. Let me know if there is any question so far. Are you following the class so far? Have you been able to launch the simulation properly? Is the goal for today's class clear? We can hear you. Audio and video are good. Yes, yes, it's clear. How do I open the terminal? Asks Leandro. Very easy. You have to come here to the bottom menu and click on this icon that you see here. Actually, this is also pointed out here in the notebook. Yeah. But here in the bottom menu, you click on the very first icon, actually. Yeah. If you click here, this is going to open a terminal. Okay. Like this one. And you can open as many as you want. So in fact, we are going to open a second one already because we are going to leave this one here running because it is the one that it's running the simulation. And here we are going to open a second one so that we can execute other commands, right? Okay, then let's keep going. So the very first thing, the very first step is to create our ROS2 package. Yeah, so we are going to create a new package where we are going to be placing our code, okay, for creating the line following program. Yeah, then again, you have the command here to create the package. You have the commands here in the notebook, so you can directly copy them from the notebook and paste them into the terminal, yeah? So for instance, first command, very important, to go inside the SRC folder of the ROS2 workspace, and once we are in there, we can execute the command in order to create the new ROS2 package, yeah? So you can see we are going to name our package line_navigation, and we are adding some dependencies to our package, such as CV2, CV bridge, which we already introduced at the beginning, etc. Okay? Actually, there is a typo here. This is not RCL-LPy. It's RCL-Py. Okay. There we go. All right. So now we have created our line navigation package. Yeah? Now, let's open another tool available here in the project, which is the code editor. And you can do that also very easily just by clicking in the icon that you have right at the right side of the terminal icon. Yeah, this is one here which says code editor. Let's click here, and this is going to open a graphical code editor, which is going to show us here all the different folders, workspaces that we have in our project, in this project, okay? Now, in this case, we are working inside the ROS2 workspace, so let's go inside the ROS2 workspace. Now, inside the SRC folder, and here we are going to find the new package that we have just created, line navigation. All right? So, what else? Then, the very first thing that we are going to be doing is to add a new Python script, which we are going to name line_navigation.py. okay? And as you can see here from the image, you have to add this Python script inside the line navigation folder, which is inside the line navigation package, yeah? So we have the line navigation package here, and inside we have another line navigation folder, which already contains this init.py file. So inside this folder, we are going to create our Python script, yeah? And we can do this very easily, for instance, by right-clicking in this folder, selecting the new file option, and then just introducing the name that we want to give to the file, which in this case is going to be line_navigation.py. There we go. Okay, so we have our Python script, which right now it's empty, and then we are going to start filling it up with some basic code, yeah? So again, you have the code here in the notebook, so what we are going to do is to copy the code from the notebook and paste it into the script here using the code editor, okay? There we go. All right, so this is the very first version of the program. Let's, before quickly explaining what we are doing here, which is very basic, we are going to edit also the setup.py file, yeah? This setup.py file, you are going to find this file located inside the line. Sorry, let me drink a little bit. You are going to find this setup file inside the line navigation package. And basically, what we are going to do also here is to edit this file in order to add this line here, yeah? So basically, everything that we are doing is to add this line here, but actually just for simplicity, we are just going to copy the whole file from the notebook and replace it here in the code editor, okay? And this is the important line that we have here, where basically we are generating this line navigation node executable, yeah, from the Python script that we have just created here, yeah? So we are going to build this Python script into an executable named line navigation node, okay? This is what we are doing here. All right. Now, before building and testing this very first version of the program, let's have a quick look in order to see what we are doing here. So basically, what we are doing here is to create a class named ImageSubscriber. And this class, of course, has a constructor. And inside this constructor, what we are doing is to define a ROS2 subscriber. Yeah, right here. And we are subscribing, in this case, to this particular topic. Camera/image raw. Yeah? And what is this topic? Well, basically, this topic is the topic where the camera of our robot is publishing the images. Yeah? So our robot, yeah, has a camera here in the front of the robot, in the front side. And this camera is capturing images, right? And then what it is doing is to publish these images into this topic. So what we want to do actually is to have access to these images, right? Because we want to process and know what the robot is seeing. So for that, what we do is to create a subscriber for this topic, okay? If you attended to the last week class where we were talking about April tags and so on, you already know all this, yeah? Because basically it's the same. So we are subscribing to the camera, and also we are creating here an instance of the CV bridge, okay? Yeah? The CV bridge, as we explained it earlier, is going to allow us to properly integrate OpenCV with ROS, okay? Now, for our subscriber, we have a callback function, which is defined right here. Then what are we doing in this callback function? Again, I already explained this for last week's class, but I'm going to explain it again, okay? No worries. Just for all the new people who didn't attend, I'm going to explain it again. So basically what we are doing here is to convert the image from ROS format to CV format. Yeah? We are using the CV bridge that we have initialized right here in order to convert the images from a ROS format to a CV format. Okay? Somebody asked in last week's class, why we need to do this? Well, we need to do this basically so that we are able to process the data using OpenCV methods. Yeah? Then, once we have converted the image from ROS format to CV format using this method, what we are doing is to use the EMShow or image show method in order to display the image. Okay? And basically that's it. Yeah? So basically what we are doing here is to subscribe to the camera topic to get the images, and then for each image that we receive, we convert it to CV2 format, and then we display it using the image show method. Okay? Basically, that's it. Then let's build our program and test it very quickly. So again, we have the commands here. So we go, let me copy the commands from here and paste them to the terminal. There we go. So we go to the ROS2 workspace directory in order to be able to run the Qualcomm build command, and then we build our line navigation package, right? So let's go for it. And then once we finish building our package, what we are going to do is to source the workspace. Here we go. Source the workspace, and then execute our program using the ROS2run command. Yeah? So let's execute our program, and basically what we should see here is a display with the images that the robot is capturing. There we go. Okay? So this is exactly what the camera of the robot is capturing right now. As you can see, we can perfectly see and visualize here the blue line in the floor, which is the one that we are going to be focusing for today's class. Okay? Yeah? All right. So far, so good. Any issues? Let me have a quick look here at the chat. Clear. How did you add the line navigation py file? Okay, I can see that Tisas has already answered to you. From copy paste, syntax error. Okay. If you are getting some weird error from copy paste, what I suggest, Ivan, is that you remove the file completely, okay? Remove everything. Make sure that you don't have any character here, and then copy and paste it again, okay? I would suggest to select the code manually, like this, instead of using this tool, okay? Because this is an automatic copy and paste tool, but sometimes, depending on the system that you are using, it can give some problems, yeah? So my suggestion would be to come directly here, select everything, and then you can just Control-C and Control-V, okay? There shouldn't be any issues if you follow this method. All right. So let's keep advancing. Okay. Then we have created a basic ROS2 program where we are using the CV bridge in order to capture the images from ROS, convert them to CV2 format, and then display them. All right? Now, this is very cool, but actually there are many things here in this image which we don't care right now. Yeah? Why? Because what we are interested in is basically this blue line that we have here, right? Then this brings us to the concept of color space. Yeah? So color space in robotics refers to a method used to represent colors in a way that is easily understandable and computationally efficient for machines. Yeah? So the typical color space, the one that probably everybody knows, is RGB, right? Which is basically based on all the colors being represented on a combination of red, green, and blue, right? Now, the one that we are going to be using, and one that is very extended in robotics, is the HSV color space, which letters go for hue, saturation, value. Yeah? This is very typical in robotics. Why? Well, because it has some interesting advantages, like, for instance, it is much less prompt to errors when there are changes in the lighting. Yeah? So for instance, the RGB image that we can see here, it is very clear, right? But if we change the light that we are applying to this apple, if we increase the light or if we decrease the light, this is going to change a lot. Yeah? And this in robotics sometimes can be a little bit problematic, right? So HSV, on the other hand, represents the colors using different standards. For instance, the hue represents the type of color and is measured in degrees around a color wheel. Okay? So this hue basically is going to represent which color it is, let's say. Yeah? Now we have the S, which stands for saturation, and which represents the intensity of purity of the color. And this is typically expressed as a percentage. And finally, we have the V, which stands for value, and which represents the brightness of the color. Yeah? Here you can see a comparison between an RGB image and an HSV image. And in robotics, lots of times you are going to see this HSV format or color space being used. All right? Then, once we have the image converted to this HSV format, what we are going to do is to try to isolate the color that we are interested in, which in our case is blue. Yeah? And how can we isolate the color blue from this image? Well, that is done typically by using what is known as a color mask. Okay? Or a binary mask. Yeah? So, in OpenCV, a binary mask is a type of image where each pixel is either black or white. Yeah? And this is used a lot in order to isolate or to represent specific regions of interest inside an image. Okay? Then, what we are going to achieve with this is that the mask is going to make it easier to extract and work with a specific object or region of an image. Yeah? Then, summarizing, what are we going to try to do right now? First of all, we are going to convert the image from the typical RGB format to HSV. Okay? Now, we are going to define a threshold, values, that correspond to the blue color. Yeah? So we are going to focus only on the parts of the image which are blue. Okay? Let's say it like this. And then we are going to create a binary mask where pixels within the specified HSV blue range are set to white and all others are set to black. Okay, so we are going to isolate the image so that we only focus on that specific part. Yeah, which in our case, again, is the blue line. Okay, then this is the code that we are going to be adding. Yeah, so let's copy all this piece of code here from the notebook again. and replace it in our line navigation script. So let's select everything, remove, and paste the new code. Now, very quickly, let's see how all these concepts that we have been introduced are translated here into Python code, right? So again, we have our class with the constructor where we are subscribing to the camera topic, and we are initiating our CV bridge, okay? This is exactly the same, nothing changed here. Now, inside the camera callback is where we have added some things, okay? Then, first of all, as before, we start by converting the image from ROS format to OpenCV format, okay? First step. Now, we convert the image from RGB color space to HSV color space. Okay, this is what we are doing here, and for this we use the CBT color method. Okay? Yeah? And then this is going to output an image in the HSV color space that we are storing here in this variable, right? Now, here we are defining the threshold for what we are going to consider blue in our image, yeah? So this is a lower value, yeah? A lower bound or a lower threshold, and this is an upper threshold, yeah? So any pixels which are inside this range, we are going to consider them as blue. Okay? This is what we are doing here. Defining the range of that defines the blue color in the HSV image. Okay? Now, once we do this, what we do is to create the binary mask. Yeah? So we use this in-range method, right? And then we pass the image in the HSV color space and the lower and upper boundaries for blue, yeah? And then this is going to create the binary mask, yeah? So basically everything which is within these values is going to be white, and everything red, everything else in the image is going to be black, okay? And then here finally we apply the mask to the original image. Yeah? So once we have defined the blue mask, we apply it to the original image, which is this, we have it in this current frame. Yeah? Okay, and then at the end of all these, we are going to again display our image so that we can see what is the final result, right? Okay, excellent. Then let's build again our package because we have updated the code, so we need to rebuild it. Then let's source here our workspace, and finally let's run again our program to see what we get. Now, what is the final result of all this? Okay, so as you can see here we have the blue line which appeared in the original image, and everything else is black, yeah? So this is the only thing for our mission, for our goal for today's class. This is the only part of the image in which we are interested, yeah? So we have applied the binary mask, and then here in the final resulting image, we only have our blue line, yeah? So far so good. Are you following? Have you been able to get the same result as I? Selecting worker, that tool is broken. Nice to hear that. Are those numbers determined by experimentation for the HSV value? Yes, basically. I mean, you can know some values, but at the end, it's going to depend in each scenario. So you might need to make the boundaries a bit more stretch or make them a little bit higher. It depends on experimentation, basically, yeah. Gilbert is already doing the homework. Oh man, you are an advanced student already. Okay, all right, then let's keep going. Okay, so now we have been able to, let's say, isolate the blue lane from the image, yeah? So what is going to be the next step? Well, the next step actually is to detect the line as a line, okay? Or in other words, to be able to extract more information about this line, yeah? Then basically here we are going to focus on two things. We want to get the contour of the line, yeah? The contour being, let's say, as you can see here, the borders of the lines, of the blue line, right? Then having the contour of the line, we are going to be able to extract what is known as the centroid. Okay? Then let's go step by step. So, so first of all, the contours in image processing are curves joining continuous points having the same color or intensity. Yeah, you can see a graphical example which is easier to understand here. Yeah, and the concept of contours is crucial. It's very important in computer vision, for instance, for shape analysis or object detection. Yeah. Then, once we have the contours of, in this case, in our case, our line, we can then calculate what is called the centroid. What is the centroid? The centroid, in this case, is the geometric center of the detected contour. Okay? So, for instance, in this case, the centroid would be the point in the center of these coins, right? That would be the centroid of the contour, right? Then, what are we going to do? Let's clarify the steps, the next step to follow. So, first of all, we are going to find the contours of our line. Yeah? For this, we will use the find contours method. We are going to see it in a moment in the code. Second, we are going to iterate over the detected contours and compute its moments using the moments method. Because this method is going to provide us the centroid of the contour, okay? So the moments, as you can see, include quantities like the area of the contour, the centroid, and more information. We are going to extract the centroid, exactly, and once we have the information of the centroid, we are going to draw up a point, let's say a circle, where we have computed the centroid, okay? And in the final step, we are going to display the resulting final image, okay? Then, for this, we are going to add a new method to our class, which is here, we have it defined here. It's this get contour data method, okay? Then, let's copy this. And paste it here, add it to our class, okay? So I'm going to go here after the listener callback method. Down here and here I'm going to add the new method. Okay, so as you can see here from the comments, the purpose of this method is to return the centroid of the largest contour in the binary image mask, yeah? So here we are defining a constant, a variable, which is this mean area track, which basically stands for the minimum area for track marks, okay? So we are going to come back later to this value because It's going to be important, okay? But basically, you can think of this number as a filter, yeah, a lower pass filter, yeah? So in order for our program to consider something, not something, so in order for our program to consider a part of the image as something to track, yeah, it has to at least be higher than this number, yeah? So anything which doesn't reach this number is not going to be considered, yeah? Because we are going to consider that it's some error that can appear in the image, yeah? So we are not going to process it. We are going to discard it, okay? So this is what we are going to do. For instance, so in the image, at some moments, we can find some blue points which are in the background, right? Yeah, so let me get an image. Yeah, so here we cannot see it, but maybe, yeah. So for instance, in this case, are we interested in analyzing these tiny blue points that we have in our image? No, right? What we are interested is in the line that we have right here, yeah? Then all these blue points, which are part of the line, but it's here, so we don't have direct vision right now, and we are not interested right now, yeah? So all these, we can consider it as error, and then we are going to use this value here in order to filter out all these small blue pixels that we get in the image, okay? This is the idea of this variable. Then we are using the find contours method, as already explained, in order to find the contours, yeah? Exactly. And then for every contour that we detect, here we are going to iterate over them and get the moments, yeah? And then if the moment is higher than the threshold that we defined earlier, we are going to decide that the contour is part of the track. Okay, it's part of the line that we want to follow right now. Okay? Then there is a second part here, let's go back, here, that we need to add also to our camera callback. It's here. Yeah? So let's add also this to our callback function. Where are we going to add it? We are going to add it here, right before the image show, okay? Right before we display the image. So let's add it here, okay? Then basically what we are doing here is to call this getContourData method, and we provide to it the blue mask. Yeah, the blue mask contains the information of the blue lane that we are trying to follow, yeah? And then if we get a result, what we are going to do is to draw a circle in our image. Okay, we are going to draw a circle in order to basically point where the centroid is. Yeah? Okay, let's compile this and we are going to see it clear because it's something like this. Yeah, so this is the blue mask with the lane and this is the centroid of the image. Okay? Then, if we have done things correctly, we should get the same result as we can see here in the notebook. Okay, there we go. Let's source and let's run again our program. Okay, and there we go, right? So we have our image with the binary mask applied, Yeah? And then here we are drawing the centroid of the line. Okay? Great. So we have almost everything. We are already detecting the blue lane. We are able to apply a binary mask so that we focus only in the blue lane that we want to follow. We are able to get the contour data of this lane, and we are able to compute the centroid. Yeah? So what now? Well, now what we are going to do is to use this centroid in order to send velocity commands to the robot. Yeah? So basically our goal is to make our robot follow this centroid, right? So how are we going to do this? Well, basically knowing where the centroid is, we can know the error, yeah, with respect to the center of the image. Yeah? Then ideally what we want is that the centroid of the lane is always in the center of the image, right? Because this means that we are properly following the lane. Yeah? When we have the centroid in the center of the image, it means that we are properly following the lane. Yeah? If it's not in the center, it means that we need to move a little bit the robot. Then we are going to use this error of the centroid with respect to the center of the image in order to compute the angular velocities of the robot. Yeah? So we are going to keep a constant linear velocity, but we are going to be changing the angular velocities based on this. Okay? So here we have a more technical information. Yeah? So there are many methods of implementing this part, such as a PID controller or model predictive control. But yeah, so that is a little bit too complicated for an open class. So what we are going to do is a simple proportional control algorithm based on the calculated displacement error from the center point of the input image multiplied by a proportional constant. Okay? So, as I was saying, we are going to move the robot forward at a fixed linear velocity and only make changes to the angular velocity. Yeah? So, the formula used is going to be like this. Yeah? Error is equals to x minus the width divided by 2. So, basically summarizing, this is the deviation from the center point. Yeah? So, how much deviated is the centroid of the lane from the center of the image, basically. Okay, summarizing. Then, for this, we are going to add we need to add some things to our program, right? Then, first of all, we are going to add some constants, like the linear speed and the proportional constant. There we go. So let me copy this and add it to my code. This, we can add it, for instance, here at the beginning, right here. Then, of course, very important, we have to add a ROS to publisher, yeah? So, we are going to copy also this and add it, in this case, to the constructor. Yeah, we are going to add it here in the constructor of our class. So we need to define a ROS to publisher that publishes twist messages to the command bell topic. By the way, I am seeing now here because there is this warning. So we also need to import the twist message, right? I think this is not explained here in the notebook, but yeah, important. We also need to import the twist message, okay? So I'm going to do this manually here. Then very easy. From geometry messages dot message import twist. Okay, there we go. Okay. And then finally we have to add all the calculation of the angular velocity to our callback. Yeah? Then let's add this here to our callback. So where are we going to add this? We are going to add it. Actually, I think that here we already have this line and everything, right? To draw the circle. Okay, yeah. Then we are going to replace basically this part here with the if line. We are going to remove this and replace it with all our code, yeah? So we define the twist message. We get the width of the image, and then we compute the error, right, from the width. Then with this, again, this is the same as we had before, where we are drawing the circle, okay, the centroid. Okay, yeah, and then finally we multiply the error value by this proportional constant, okay? And then once we have the exact value that we want, this also you can play a little bit with this value, yeah? This KP value, you can play a little bit in order to improve how the robot turns, okay? So this is not a magical number that has to be this. This is something that you can use also to play a little bit with this, okay? And then finally we just publish, right, our twist message so that the robot starts moving using our angular velocity computed from the centroid and the fixed linear velocity. Yeah? Does it make sense? Do you understand what we are doing here? Let me go back here to the chat. I can see. Okay, let me go back here. Where did you paste the new lines of code? Right above the C, exactly. Right above the C, the image show. Yeah. Yeah, here Thisas also has shared the line, in case that you want to copy paste it here from the chat, in order to import the twist message. Ivan says, yep, moving around, right into a wall. Okay. Leandro says, yeah. Okay, so I see that you are starting to test it. Then let me build it myself and test it. Because it's not going to work already very good, okay? Then let me build my program very quickly and try it out myself. So let me rebuild here my package. Source. Okay. And run our program. Okay. So now I'm going to put the simulation here, and I'm going to put, okay. Very important. Let's see what's going on here, okay? Very important. So we can see that the robot starts. Okay, so right now it's like moving left, right, try to compensate all the time from the centroid, okay? So probably this could be fixed with a better KP value. Okay, but... Okay, so let me do one thing, okay? Let me rerun this, because, yeah, this can happen, but this is not the behavior that we should be getting. So let me restart everything. By the way, how to restart everything? Just close the program, close the simulation, okay? In case that you get your robot like this crazy, don't worry, just stop the simulation. You are going to see that even though after pressing Ctrl+C, maybe the client doesn't die, okay? So for this, you have here inside the simulation workspace and a script that is this kill_gz.sh that you can run in order to kill all the gazebo processes, okay? See? So once you execute it, you are going to kill all the gazebo processes, and then you can safely run again the simulation. There we go. I am getting a strange view, so let me actually restart it. So let me kill it again. Okay, there we go. All right. So let me try to run again my program very quickly. Okay, let me verify that everything is correct here, and then I don't have anything strange. Because I was copy pasting here very quickly, and I might have done something wrong. So let me just review it. Okay, so we are getting the contour. Okay, we have the blue segmented image. If lane, we compute the error. Yeah, I think this is right. I'm not missing anything, I think. Let me recheck from here. Yep, okay. Okay, then let's go for it. Yeah, let me just rebuild to make sure that I have the latest version. Okay, source. Okay, then let's open here this. Okay, there we go. Okay, so now as you can see, it is much more stable. And it's trying to follow here the centroid of the image. There it goes, now it's turning, and now it should keep moving forward. There it goes. Okay, and now this is the interesting part. As you can see, instead of continue with the line that it had in front, it has changed to compute the centroid of some of the lines that we had here at the, which are further away. Yeah? So, this is an issue. Does somebody know? Yeah, and actually this is expected, okay? This is the challenge that we have here, yeah? So, as I was explaining, the issue seems to be that it detects a line that is very far away and goes to that one instead. You can see the behavior here, yeah? So, right now it's following this lane, but then at some point it just, no, this is the fixed behavior. This is the wrong behavior. Yeah, the one that we had. So it starts following this lane, but at some point it switches from the current lane to one of these lanes which are here far away, right? There it goes, yeah? And then obviously this messes up everything, okay? So does somebody know or have a suggestion of how we can fix this behavior? Write it down in the chat, please. Leandro says, greater area. What do you mean with that? What do you mean with greater area? Can you be more specific? Gilbert says, make mean area track value smaller. Close. Close. That is close. Actually, that would make sense. Leandro says, to avoid taking into account the little one far away. Okay. Okay, so actually, it's a combination of what Leandro is saying and what Gilbert is saying, right? So actually, it's to make the mean area track higher, not smaller, okay? So, thinking quickly, you might think that you should make it smaller, but actually you have to make it bigger. So Syed says, make it bigger so that it sees less of the lines that are farther away. Exactly. Exactly. So if we make this value higher, yeah, so remember that this is a threshold value, yeah? So if we make this higher, for instance, let's say, I don't know, I'm going to make it to 1,000, okay? This is the value that Thesis has been testing, so I'm going to use this one. So if we make this value higher, what we are going to do is to discard any potential errors, yeah, or lines that might be appearing which are not the main line, yeah? So this is why we need to actually make it higher, yeah? Does it make sense? Do you guys understand this point? Yeah? Sure, says Leandro. Okay. Awesome. Okay, then let's. Okay, but this is just my word. Okay, then let's see if this actually has some impact. So actually, let me stop everything. Let me restart the simulation too. I need to. Okay, I have already done this modification, right? I have increased the value, and then I'm going to recompile. And here, let me just again kill the gazebo processes and restart the simulation. There we go. Okay, there we go. Let's source and let's run again our program. Let's see if we have a different behavior now. Okay. So there we go. The robot is centering the centroid. We start following the lane. Okay, so far so good. Now we are going to start turning. There we go. Now we start following this line, and we should keep following this line until the end, right? So let's see if this works. Yeah, so we keep moving forward. Okay, we keep moving forward. So this is looking good, right? We are not getting that error where we were moving, the centroid was moving to lines that are farther away, yeah? So we are sticking with the main line now. So now is where we have the problem, because what happens now? That we have lines to both sides, right? So basically our algorithm doesn't handle this kind of situation and doesn't know where to go. Should I go to the left? Should I go to the right? It doesn't know what to do, okay? And this is basically the homework that I'm going to put you, that Tisas and I are going to put to you, okay? So you need to figure out a way in which to modify, to improve this program so that it is able to handle these kind of situations. When a line finishes and there is a bifurcation, yeah? So the line goes to the left and to the right? You need to modify, to improve the algorithm so that it is able to handle these kind of situations, okay? In this case, ideally, you should make it go to the left because we are interested in reaching the unloading area, let's say, which is this corner here, okay? But you can use different techniques. I leave that to you, okay? But use the algorithm, modify some of the methods like the get control data, the camera callback, the listener callback, etc. Modify, play, test, whatever, but improve this algorithm so that it is able to handle these kind of situations. Okay? So this is the homework that we put to you. And as always, we would be super, super happy that you are able to solve it and record some images, videos, and share it with us in our social networks. Yeah? We would be super, super happy to see that. So yeah, from my side, I'm going to leave it here. Let me check if there is any final messages here. Johnny says, a beginner here. No worries, Johnny. In these open classes, we welcome everybody. Beginners, intermediates, advanced, so no worry. Okay, we have Tomás here sharing his thoughts in Spanish. But yeah, so basically he's saying that we should force the algorithm to look for a thicker line, right? And not a tinier. Basically, that is what we are doing by increasing the area. Yeah, so basically small number means thinner lines allowed. Exactly. Tomás says that I am a very good teacher. Thank you very much, Tomás. Thank you very much. Do you say, when will the next lesson be? It's going to be next Tuesday. Duigu, okay? So these open classes, unless we say otherwise, we are doing them every Tuesday, same time, okay? Every Tuesday, 18 CET. So the next open class is expected to be next Tuesday at 18 CET. All right, guys, so one more time, thanks to all of you for being here with me in the class. I hope that you liked it. I hope that you enjoyed it. I hope that you have learned something from it. I hope to see you all in the next class, next Tuesday. And yeah, as always, until then, keep pushing your ROS learning. So, see you.